Voltmeter is a device which is used to measure the PD between 2 points. Hence, it is connected in parallel across the 2 points between which you need to measure the PD. Its introduction should not alter the main current, so it should offer as large a resistance as possible. The resistance of an ideal voltmeter is infinity. You have worked with an ideal voltmeter, which is that potentiometer. Let us suppose this is a part of a circuit. The resistance is R. You want to measure the PD across this due to the passage of current in that. You connect a voltmeter in parallel with this. Now our problem is to convert a galvanometer into a voltmeter. What you should do? You have to increase the resistance. To increase the resistance, what you do is connect a resistance in series with that. In fact, I will call this resistance as R. Okay. I will call this resistance as R. Let me call the current through this as Ig. This is the current driven through this by the PD, V, remember it. Clear? This is the current Ig driven through the voltmeter by the PD across this. That high resistance, they call it multiplier, I think. How to find the value of that? V is equal to Ig into G plus R. So, V by Ig is equal to G plus R, or R is equal to V by Ig minus G. So, if you connect a resistance R given by this formula in series with a galvanometer of resistance capital G ohms, then a current Ig passes through that, it reads a voltage V. Clear? Now, by mistake, suppose you connect a voltmeter in series instead of connecting it in parallel, what could happen? If it is ideal voltmeter, of course, it will have infinite resistance, no current will flow. Otherwise, there is a current flowing, but you will get all wrong readings, remember it. You will get all wrong readings. Unlike in the case of a ammeter, where the ammeter will be spoiled, remember. So, we will be working out problems on conversion of galvanometer into voltmeter, conversion of galvanometer into ammeter, etc. in the problem solving session. Okay. Now, we will take up the next chapter. This is electromagnetic induction. Electromagnetic induction. We have already seen the discovery of Ørsted that a current carrying conductor is surrounded by a magnetic field, which was announced in 1820. Soon after that, they thought of observing the reverse possibility. What is that? Place a conductor in a magnetic field, will there be a current flowing through it? If you pass a current through a conductor, there is a magnetic field. So, what is the complementary effect? Place a conductor in the magnetic field, there should be current now. Of course, if you can get current like that, we will have unlimited supply of energy, isn't it? From the law of conservation of energy, this is not possible. If you keep a conductor motionless in a magnetic field, if current can be produced, it goes against the law of conservation of energy, isn't it? There is no free meal, remember. So, you have to supply energy either to a magnet or to the conductor. So, in this direction, experiments were conduct it, and Michael Faraday's two famous experiments, you are all, I am sure by this time, familiar with those experiments. What are they? Do you remember? Has it not been discussed in your regular class, electromagnetic induction? Huh? Discuss now. The two experiments are, one is what we call coil and magnet experiment, and another is coil and coil experiment. Tell me, have you not gone through this? You know the results of this now? Huh? You are not responding at all, I can't make out. Have you seen these experiments discussed? Okay. Now, the results or the observations in these two experiments were put in the form of two laws by Michael Faraday. What he observed was, whenever there was a relative motion between a coil and a magnet, there is a voltage produced in the coil. If the coil forms a closed circuit, there will be a current flowing, remember it. Here, whenever there is a current getting broken or established in one of the coils called primary, a EMF and therefore a current, if the secondary coil is closed, will appear in the secondary. Now, the results of these two experiments or the observations were put in the form of two laws by Michael Faraday. These are what we call Faraday's laws of electromagnetic induction. What the first law says, he said, whenever you move a magnet near a stationary coil or move a coil near a stationary magnet or move both, there is a change in the magnetic field linked with the coil. This change is responsible for producing the EMF in the coil. The EMF produced in a coil due to the change in magnetic field associated with it is what we call induced EMF, and the phenomenon is called electromagnetic induction, getting electricity from magnetism, remember it. We picture this magnetic field in terms of field lines, and therefore change in magnetic field is pictured in terms of change in the number of field lines linked with the coil. The total number of field lines linked with the coil is what we call magnetic flux, and therefore the first law was put in the form like this. Whenever there is a change in the magnetic flux linked with a conductor, an EMF is induced, the EMF lasting as long as the change in the flux takes place. That was the first law. The second law was, if you move the magnet faster near the coil or move the coil faster near the magnet, you find a greater EMF induced. This was put in the form of a law as the induced EMF is directly proportional to the rate of change of magnetic flux. Or you can put it in a mathematical form, induced EMF is directly proportional to rate of change of magnetic flux, or in SI unit we take this constant as 1 and write it as E equal to d phi by dt, remember it, where phi is the flux link. Now, suppose the conductor is in the form of a coil having n turns. With every turn, this much of flux is linked. With the n turn, you can expect n into this much, so that the induced EMF can be written as d by E equal to d by dt of n phi. That n phi is what we call flux linkage. N phi is called flux linkage. This relation is what we call flux rule. It is also called Neumann's law. You have also seen that usually this is put in the form with a minus sign here, right? What is the meaning of that minus sign there? the EMF is induced in such a direction so as to oppose the cause producing it. In fact, it was given in the form of a law by a fellow named Emil Lenz, I think. It's called Lenz's law, it's not. It's called Lenz's law, remember it. Negative sign signifies Lenz's law, and you can argue that Lenz's law is nothing but a statement on the law of conservation of energy. Law of conservation of energy. You need to do work, that is what it says. The work done is converted into electrical energy. Is it clear? To put it in a very simple way, it's like this. Suppose you have a circular coil, circular ring, say. You take a magnet with the north pole facing the ring, suddenly thrust it near this. The flux linked with this will change, therefore an EMF is induced and therefore a current will flow. In which direction the current should flow? According to Lenz's law, it should oppose the cause producing it. What is the cause producing it? Approach of the north pole. That should be opposed. That means current is induced on this side such that this face becomes a north pole, because there is repulsion between the two north pole. When north pole comes, approaches the ring, current should flow in such a direction that this becomes a north pole. The easy way to remember is current flows in the anti-clockwise direction on this side in that case. It's very easy to remember. Suppose you pull the magnet. When you pull the magnet out, what will happen? The flux linked with this will change. The current should be in such a direction so as to oppose that change. That means the decrease must be arrested, no? So what do you expect then? When you pull the north pole away, current must flow in this in such a direction. It prevents the, correct, no? That means this north pole should be getting attracted by the, this face becomes the south pole. Clear? This is how you can. Remember, in Lenz's law, you talk of current. Current is induced in such a direction so as to oppose the cause producing it, you say. Isn't that? You speak of current. That means it should be a complete circuit. Lenz's law, therefore, is applicable to closed circuit. So, if the circuit is not closed, open, then you have to consider in which direction current would have flown if the circuit were closed. In that direction, EMF is induced. Now, what all things we have said, we will try to put this in a quantitative form, say. Let us suppose I have a flat surface of area A, say. This area can be represented as a vector quantity. Okay? I have a flat surface of area A. I place it in a magnetic field, uniform magnetic field, say, which is directed like this. And let us suppose the angle between them is theta. Magnetic flux linked with this is defined as phi is equal to B dot A. Phi is equal to B dot A, which is of course B A cos theta. As you can see, when theta is 0, that means when the field is directed normal to the surface, maximum flux is linked. When theta is 90, no flux is linked. In general, you can say this is the flux linked. So, what is the magnitude of the induced EMF? Magnitude of the induced EMF is d by dt of phi, which is d by dt of B A cos theta, right? Or this you can write it as correct? You see 3 possibilities. In this, you say flux changes because there is a change in the magnetic field. There is a change in the magnetic field. In the case of, for example, a coil and magnet experiment, it means either the coil is moving with the magnet is at rest, or the magnet is moving with the coil at rest, or both the coil and magnet are moving relative to each other, or in the coil and coil experiment, current in the primary is changing, that produces a changing magnetic field linked with the secondary. So, this says field is time dependent. This says area is time dependent. For example, let us suppose there is a magnetic field, uniform magnetic field directed perpendicular to this board, and here you have kept a circular ring set. Suddenly you stretch it, hold it at the ends of the diameter and stretch it. The area changes, no, an EMF is induced. Or in this case, orientation is changing, field is same, field is not changing, area is not changing, but the orientation of the conductor or loop with respect to the field is changing. In a given situation, any one of these may be happening, or all the 3 or any 2 of those may be happening. Now, the EMF induced in each of these cases, the mechanism by which the EMF induced may be different. The mechanism by which the EMF is induced in each of these cases may be different, but the induced EMF in all those cases is given by this formula. That is the beauty of that flux rule. Whatever may be the mechanism by which the flux is changing, the induced EMF is given by this simple rule. The next question is, how we find out, how we know that an EMF is induced in the conductor? To know whether there is EMF induced in the given conductor, you have to search for the presence of current in that, isn't it? You have to search for the presence of current in that. In the circuit that we discussed so far, the EMF was actually, localized in a small region, especially between the 2 plates of the, or 2 terminals of the battery. Clear? In the circuit with batteries, the EMF is localized between the 2 terminals of the battery. But here, when you are moving a magnet, say, what is happening is it is distributed over the entire conductor. Remember it. It is distributed over the entire conductor. A current is flowing in that. Current flowing means there must be forces acting on the charges, free charges in the conductor. Correct now? This force per unit charge is what you call electric field. This field is produced by the movement of the magnet. That means due to the change in the magnetic flux linked with the conductor. Clear? This EMF is producing a field which is what we call induced electric field. This, although exerts force on the electric charges, just like the field due to electric charges at rest or field provided by the stationary electric charges, in both cases forces are experienced by free charges, but this induced electric field has certain characteristics different from the electric field due to stationary charges. What are they? You know, in the case of electric field, due to stationary charges, lines of force have a source and a sink. They start from the positive charge and terminate on the negative charge. In this case, they are simply closed paths. In this case, it's closed paths. Secondly, the electric field produced by stationary charges, we have seen it is conservative force field. Work done is independent of path, or work done over a complete path is 0. Here we have a different situation. What is that? How do you define EMF? How do you define EMF? EMF is defined as the work done per unit charge in moving it once around a circuit, correct? No? Work done per unit charge, work done, this work is of non-electrostatic origin per unit charge, correct? Now, work done is force into displacement per unit charge, force per unit charge is, so you can put it like this now. But this is from Faraday's law, induced EMF is equal to minus d phi by dt. Of course, you can say d phi by dt in magnitude. So, what you find is that whereas in a conservative force field, work done over a complete path, this should be equal to 0, but this is not here. It is equal to EMF. In fact, this you can write it as B dot A. If A is not changing, of course, you can write it as. So you see, a changing magnetic field or a time dependent magnetic field produces a electric field. This is a very, very interesting relation between the two fields, which follows from this result, isn't it? A time dependent magnetic field produces an electric field. Now, let's come back to this. E is equal to induced EMF is given by, I can put it as 1 by Q F dot dl. Okay, where F is the force acting on the charge. Now, you know what are the forces acting in the presence of a combined electric and magnetic field? It is given by Lorentz force, correct na? Lorentz force equation. So that you can put it in the form now, induced EMF is so you see, there are two factors which contribute to this EMF. Will you agree? There are two factors which contribute to this EMF. One is this. What is that? Induced electric field. What is happening is, if you have a conductor lying motionless in a magnetic field, if the field is changing, the time dependent field, magnetic field will induce an electric field, and it is this electric field which exerts force on the free charges in the conductor. That produces that EMF. Have you understood? The second factor here, this is responsible for the production of EMF whenever there is a relative motion between the conductor and the magnetic field. In fact, this is what we call motional EMF. It's what we call motional EMF, remember it. The first one, induced electric field, produces EMF. Even if the conductor is at rest, when the magnetic field is changing with time, you have electric field induced that exerts force on the free charges in the conductor. In the second case, you find that there is a force acting on the moving charges in the magnetic field, which is responsible for motional EMF. We will find out that. Let us suppose there is a uniform magnetic field of strength B. There is a uniform magnetic field of strength B within this boundary. Of course, the magnetic field cannot abruptly terminate there, you should remember. Fringing is there, we will neglect that. The field is directed into. I take a metal frame. I take a metal frame of width L, say. Okay. And I pull it out with a velocity v, say. When I pull it out, there is an EMF induced. The EMF induced in a conductor when it is moving in a magnetic field, it's motional EMF. Let's suppose at certain instant, this was the length which was in the magnetic field, okay. At that time instant, what is the flux linked with this? Flux linked with it is, tell me, B dot A, here it is of course BA because theta is 0, cos 0 is 1. BA, what is BA? Bachelor of Arts here, how much? What is that? A. B into, hello? L into X. That is the flux linked. You are pulling it. What is the EMF induced, man? Magnitude of this induced EMF is d phi by dt. Actually, it is minus d phi by dt. We will say, we will consider the magnitude, or if you want the minus sign to be retained, I will retain it, no problem. This you can write it as BLX. B is not changing, L is not changing, X is changing with time. Correct now? Okay? This I will write it as BLV, where V is equal to minus dx by dt, you can say. Okay? Where V is the velocity. This is the induced EMF. If this is the induced EMF, what is the induced current? It's a closed path, no? What is the induced current, man? Will you agree? Now you have a problem. In which direction this current is induced? Use Lenz's law and tell me. Clockwise, why? Flux is decreasing, flux linked with this is decreasing. The decrease in flux is responsible for that induction. So, the current is induced in such a direction so as to oppose the cause producing it. So, the current is induced in such a direction that it produces a field which aids the already existing field. So, that field should be in this direction. So, current should be clockwise. So, clockwise current is flowing. Will you agree? Now, when a current is flowing through this, you expect a force to act? No. A current carrying conductor in a magnetic field experiences a force. What is the direction of the force on each of these? We will find out. What is the direction of the force on this? Okay, we will find out on this. What is the direction of the force? Forefinger in the direction of the field. Correct, no? Middle finger in the direction of the current. In which direction, man? Towards Kottar cross or towards Kapi card? Okay. On this, towards heaven or hell? 7. Correct? Correct now? On this side? Okay, see, there are forces acting, we found out. The interesting thing is, in the expression for EMF, which dimension of this loop is coming into picture? Only L, this much, isn't it? This and this doesn't come into picture at all. You see in the formula there, it's only L, which means you can say that the induced EMF is localized in this. You can take it that way. Okay, it is, this wire is cutting the lines of force as it is pulled out. So this is the current. Now, as a result of this current, there are forces acting. The force on this and the force on this being equal in magnitude and opposite in direction, you can forget them, is not. What is the force on this? What is the force on this? That force is strength of the field into current in that, into length, into sine of the angle between L and B, L and B, 90, sine 90 is 1. So, this is the B, I is B, L, V by R into L, which is B squared, L squared, V by R. Will you agree? This is the force acting, which is in this direction. If you want to pull it out, you need to supply energy from outside, isn't it? Against that force. Against that force, if you want to pull it out, you have to supply energy, no? Okay. What is the power that you need to supply? What is the formula for power? F dot. In this case, it is, you can take it as, okay, which is B squared L squared V by R into V, which is B squared L squared V squared by R. Will you agree? This is the power or energy every second you need to supply. What happens to the energy, sir? This energy is converted into electrical energy. From electrical energy you get heat energy. How much is the heat energy that is released? You can find out how much it is. I squared R, B squared L squared V squared by R squared, that is I squared, B squared L squared V squared by R squared, that is L squared into R. Just compare this. What can you say? What can you say? What power you supply, it gets converted into, clear? See, the supplied energy or the mechanical work that you do is converted into electrical energy, which gets converted into we will take up problems on calculation of this induced EMF in our problem solving session. I want to finish off this elementary theory first. Okay. Follow me carefully. Suppose you have a wire, you connect it to a battery, a constant current flows through the wire. When a constant current flows through the wire, there is a constant magnetic field generated around it. Correct? Pictured in terms of field lines, there is a fixed number of lines of force around it. Okay? Suppose the current suddenly increases, the magnetic field increases. That means the flux linked with this wire will change, no? Okay? If that happens, according to Faraday's law, whenever there is a change in the flux, an EMF is induced. In which direction it is induced? So as to oppose the cause producing it. What is the cause producing it? Increase in the flux. So it is induced in a direction so as to oppose this increase in the flux, which means this induced EMF is in the direction opposite to the applied EMF. Now, what we do is, we take that wire and make a coil out of that. You know, if you make a coil, a solenoid in air core, say, what happens is the lines of force within will crowd so that the field strength will increase, so that this effect will be very much enhanced. Clear? So, such a coil where this effect of induction is enhanced, we call it an inductor. Here what is happening is the current changing in the coil induces an EMF in the coil itself. You call it self-induction. Property of the coil is called self-inductance. It's called self-inductance. Remember it. Property of a coil by virtue of which it opposes any rise of current through it or any decay of current through it or any change of current through it is what we call self-induction. The phenomenon is called self-induction and the property is called self-inductance. Remember. We will be calculating the self-inductance of various types of coils later, but first we will consider this quantitatively. You know, the flux linked with a coil is directly proportional to the current flowing through it. Will you agree? Which means flux is equal to some constant into I, where that constant, it depends upon the geometry of the coil as well as the medium, permeability of the medium over which the coil is wound. For example, if it's an air core coil, it will have some value. If it is wound on a soft iron core, it will have a large value of L. Remember it. This is what we call self-inductance of the coil. Remember it. Now, let's take up this coil. Suppose I plot a graph of current in the coil versus time. What I expect? I have taken a coil of a number of turns, connected it to a battery. I switch on the battery. The moment I switch on, the current starts rising. As the current rises, initially the rate of change of current with time is large, you see. So, a large EMF is, you expect large EMF to be induced opposing the applied EMF, with the result the net EMF in the coil is less than the applied EMF, because there is an EMF opposing the applied EMF. No. With the lapse of time, of course, the induced EMF decreases so that the rise of current with the time will be like this. If the coil did not have this property, what would have been the situation, it would have instantaneously risen. No, it would have instantaneously, but real coils do not show that behavior. It takes some time for the current to rise. This is something like you apply a force to a mass. The acceleration will not instantaneously pick up to maximum value. It takes some time now. What is responsible for that in the case of force acting on a body? Mass or inertia, correct? No. Here also you can say this L has a property of, slowing down the growth of current. You can treat it as a measure of electrical inertia. You can treat it as a measure of electrical inertia, remember it. Clear? Now, once the current reaches a constant maximum value, then there is no induction effect because same current is flowing through the coil. No. Once the current has risen to the maximum constant value, the current remains same, no induction effect. Now, suppose you switch off now, what will happen? When you switch off, the current starts decaying. When the current starts decreasing, the magnetic field lines around it start collapsing, flux is decreasing. Again, there is a, whether it is increasing or decreasing, it is changing. No, there is a changing magnetic flux linked with the coil and EMF is induced. In which direction it is induced? So as to oppose the cause producing it. What is the cause producing it? Decrease. The cause producing it is decrease. So, the EMF is induced in such a direction so as to arrest the decrease, which means the EMF is induced in the direction of the applied EMF. It is induced in the direction of the applied EMF. So, it decreases. Interestingly, it takes longer for the current to grow and establish its maximum constant value, whereas it takes a shorter time for it to decay to zero, because when you switch off, suddenly when you switch off, the resistance in the circuit becomes infinity, no? It drops suddenly. The induced EMF is proportional to rate of change of flux. Current takes a longer time to grow, shorter time to decay means the rate of change of flux during decay is more than the rate of change of flux during growth, which means that the induced EMF during decay must be more than the induced EMF during growth. Will you agree? Further, during decay, the induced EMF is in the direction of the applied EMF. Both the EMFs are in the same direction, means the total EMF in the circuit when you switch off is much greater than the applied EMF. And this can lead to sparking at the switch point when you suddenly break the circuit. The reason is the voltage that appears across the switch points is much greater than the applied voltage. It is applied voltage plus induced voltage both in the same direction, and induced voltage during break is much greater than the applied voltage. Of course, it depends upon the current flowing in the circuit. So, the total voltage is so large, it can result in the air losing its insulating property. Dielectric breakdown of air takes place, and that results in appearance of a spark there. When you switch on, there may not be a possibility of a spark appearing because the two EMFs are in the opposite direction. When you switch off, chances of sparking are there. Okay. Now let's come back to this. L is a constant for the given coil. It is called self-inductance. In fact, how you define self-inductance here? When I equal to 1 amp, phi equal to L. Self-inductance of a coil is equal to the flux linked with it when unit current flows through it. Will you agree? When unit current flows through it. Suppose this current flowing through the coil is changing with the time. Obviously, phi will also change. If phi changes, then there will be EMF appearing across the coil, which is magnitude is given by E is equal to d phi by dt, d by dt of Li, d by dt of Li. L is a constant, so di by dt. So you see, you have another relation here to find to define self-inductance. E is equal to L di by dt. When di by dt equal to 1, E equal to 1, L equal to 1. The SI unit of self-inductance is, you must be knowing its name, Henry. The SI unit of self-inductance is Henry. How much is 1 Henry? 1 Henry is the self-inductance of a coil if an EMF of 1 volt is induced in it when the current in it is changing at the rate of 1 ampere per second. When the current in it is changing at the rate of 1 ampere per second. Of course, 1 Henry is a large unit, so we make use of smaller units. 1 millihenry, 10 to the power of minus 3 of a Henry, 1 microhenry. Usually, air core coils have low value of inductance. To get higher inductance, they wind the coil on a soft iron core. For example, in your tube light, they have, you must have seen what is called as a choke coil, you know. It's an inductance actually. It has an inductance of 1.2 Henry, say. It's wound on a soft iron core. Clear? An air core inductor is shown with a symbol like this. An air core inductor. If it is wound on an iron core, it is shown by this symbol. Now we have the relation connecting voltage and current for 3 circuit elements. What are they? For a resistor, V is equal to IR or I is equal to V by R. When a current flows through a resistor, the resistor gets heated up. There is always a dissipation of energy. A resistor can never store energy. It will dissipate energy in the form of heat. You have seen what is the relation between current and voltage for a capacitor. What is the relation between current and voltage for a capacitor? Q equal to CV. So, I equal to C dV by dt. We have seen if you apply a DC across a capacitor, dV by dt is 0, no current flows. So, a capacitor is an open circuit to DC. Clear? Coming to this inductor, what is the relation between voltage and, I'll put it as V equal to L di by dt. If you connect a DC across this inductor, DC means di by dt is DC, direct current. Suppose it remains constant in magnitude, I is constant, di by dt is, so induced voltage across it is 0, means it is a short circuit to DC, an ideal inductor, remember. An ideal inductor is a short circuit to DC. Have you understood? Remember, both this capacitor as well as inductor, they can store energy. Resistor cannot. This can store energy in the form of electric field between the plates of the capacitor. This can store the supplied energy in the form of magnetic field around the inductor. Remember, we are talking about an ideal inductor which is supposed to have only inductance and no resistance. More about this we shall see in the next class.